lecture 15. We are in lecture 15 now, so some of you might have asked, well, what happened to lecture 14? So lecture 14 is essentially currently in the form of a set of slides that are posted to the web page that I'm hoping that everybody reviews on their own, because it talks about lattice theory. It also talks a little bit about the origins of the name submodular, why are submodular functions called submodular, and it also talks a little bit about some of the stuff that we will use in a couple of lectures. But since we're behind, and I think this is somewhat of a subsidiary set of topics, I think that if everybody were to just look at those slides, then we'll be in good shape. Now, I don't think you're going to need those slides for today's lecture, but for next week in particular, the lecture 14 slides will be something that we will be drawing from. So that gives you a little bit of time. And I'm going to try, I don't want to promise this, but I'm going to try and do an additional YouTube lecture. The thing is that I still have lecture 1 to finish, because lecture 1's video failed, and I can't post lecture 1's video yet until I re-record it, or at least re-record parts of it, because parts of it just didn't record. And then I could do lecture 14 as a YouTube video. And then next Monday, as you know, is a holiday. But since we're one lecture behind because I was in Iceland, I'm going to do next Monday's lecture next Monday, just as a YouTube lecture. So you don't need to come to class, but basically I'll assume on Wednesday that everybody has seen on Monday's lecture. So in some sense, that means that we would need to have 3 YouTube lectures. And I'm not sure if that's feasible, but we'll see. So as I said, everyone should read the lecture 14 slides, because we're going to need them for next week's stuff. This is lecture 15. Office hours. So today's actually a pretty important lecture, because we're going to be, if we get through everything what we want to, we're going to actually define our first submodular function minimization procedure. And it's going to essentially be a quadratic programming problem. And quadratic programming is going to solve submodular function minimization. But we're going to use all of the tools that we've been looking at, that we've been discussing, namely the supp, the base polytope, and the sat, and the dep, and all of these other operators. And by looking at these definitions and what they mean, and these various different forms of looking at them, we'll be able to actually prove that the min-norm algorithm gives us the minimum of the submodular function. Now there's going to be another way that we're going to look at the min-norm algorithm after we've defined the Laplace extension, which hopefully also we'll get a chance to define today. And those of you who are interested in submodular functions, which I assume is all of you, probably have been eagerly on the edge of your seats waiting to hear about the Laplace extension, because people in machine learning talk about it so much these days. So maybe we'll get to that today, but at the very latest, we'll get to that on Wednesday's lecture. So let's do a brief summary of where we are at. We have the notion of the most violated inequality, which is a submodular function minimization problem. We have been looking at concepts for polymatroids, gaining inspiration from matroids, and that includes things like the fundamental circuit of a matroid, or the set of fundamental circuits. This particular one is one where it's based on I, which is an independent set, and E, which is something that is in I's span but doesn't include I. We saw that the minimizers of the submodular function form a lattice. The whole notion of the minimal and the maximal element of a lattice. So this minimal and maximal element of a lattice is something that's discussed at length in lecture 14 slides, which, like I said, I'm not going to have actually a live lecture on that. But it also talks about how essentially, gives you a very precise definition of a lattice, and it also talks about partial orders of sets and how partial orders lead to lattices, these algebraic structures that we've been calling lattices, and talks about a number of other things that are very interesting. The notion of X being an extreme point, and X tight sets, and maximal and minimal tight sets, essentially as being forms of a lattice. And for the most part, we really care about X. We really care about these definitions when X is one of the extreme points, or at least on the base. We have the sat function, and how it generalizes the matroid closure. The saturation capacity, which is for those elements not in sat, how much more you can move within the polytope, not leaving the polytope in that particular directions that are not in the sat set. the notion of the E-containing tight sets, which constructs a sublattice, and then also the depth function, which is kind of like we saw as a generalization of the fundamental circuit of a matroid. And we also saw, if you remember last time, that we talked about how the fundamental circuit of a matroid can be defined as an exchange, as like a set of exchange elements. Namely, it is those elements that if you add something to lose independence, those elements that you can remove to regain independence. That's like an exchange element. And it's very similar to the depth function. And here are the more formal mathematical definitions of these things that we talked about. So the notion of X-tight sets, the polymatroidal closure, which we said is the biggest, it's the maximal tight set. And we also proved last time that it's equivalent to this definition. Now we're going to need both of these. In order to show min norm is true, we need to be able to use both. So this equality is important. The saturation capacity, which we defined as C hat XE, which is sort of like those elements that are not saturated, how much more we can move, like I said. In fact, we can define sat as those elements whose saturation capacity is 0. The E-containing tight sets, which is DXE, which is a subset of all tight sets for a particular X. And then dep is the minimal E-containing tight set for a polymatroid function, which generalizes a circuit. And we proved last time this equality that there were two ways of looking at it. It's basically the intersection of all E-containing tight sets, whenever E is in sat. Or we also saw it as all directions E prime, such that if we want to move in the positive E direction, we have to, or it's possible to move in the positive E direction if we simultaneously move by the same amount in the negative E prime direction. Okay, so both, like I said, for min norm, we need both of these. The things that we need are, we need this stuff, both of these, and we need this stuff. Like I said, also, we proved that last time. And so we define this lattice. And the sat lives up here, sup lives down here, and then we have the sublattice. One thing I added since last time was that this is all relative to a particular x. So if you change x to a different point in the polymatroid, then the inner two diamonds may shift. Obviously, the yellow one will still be in the green, in the middle green one, but we'll get a different sublattice and a different sub-sublattice. So this is all relative to this particular x that we're at. Okay, so let's talk a little bit about support. So now support in some sense is the easiest of the definitions because it's the one that basically just indicates which elements of a vector are non-zero. And so we have this definition. It's the standard definition of a support. And so, for example, if we chose this point here, I don't think I need to do this really, but if we chose this point here and say this was E1, then the support, and this was x, and then the support of x would just be equal to the set containing that one element E1. Okay. But on the other hand, there's a little bit of support becomes more interesting when we start talking about x being extreme points. And here's how. So now sat we know to be a tight point. Let's say that it's the largest member of this distributed lattice, and we know it's a tight set because it's the union of all tight sets all at x, right? Now, in general, support is not necessarily tight for an arbitrary x. Now, why is that? Well, I mean, just take any particular point here, like that guy. That guy is supposed to be on the bottom face of that polytope. His support is not tight at anywhere, right? There's no point at which x of a is equal to f of a for any a. But what about when we consider extreme points? When we consider like this green point here, or maybe this point, or any of these yellow points, all of which are extreme, and so on and so forth. It seems like at each one of those points that that support may in fact be tight, and in fact that's what we're about to show. When x is an extremal point, then the support, namely the non-zero elements of x, are tight, meaning that x of support is equal to f of support. Now why is that the case? Well, let's prove this. So first of all, remember that extremal points are essentially the set of points that satisfy this set of linear inequalities that we were able to obtain by Gaussian elimination. Namely, for example, we they satisfy all of these equations. These are all of the tight elements of the extreme points, right? And therefore, if EI is a particular direction, if that's in the support, then that basically means that since the extreme point was obtained by taking these conditional valuations of the submodular function, if it's in the support, it means that that conditional valuation must be greater than 0 by definition of the support. Support is the non-zero elements. Okay. Now, if we take a direction, say EI, which is not in the support, that means that its element is 0. So then if we evaluate EK, so k is greater than I, right? If we evaluate EK at x, then we can take it out and we get the same valuation. X is a modular function since it doesn't add anything, right? So x of EK is equal to x of EK minus EI, right? Now what about f? In order for this to be tight, we need to make sure that the f valuation is the same as well. Now if we look at f, well, we know that x of EI, when it's not in the support, is equal to 0, right? Which has to be the valuation here, right? Because that's the valuation of x, because x is an extremal point. It has to be that particular value. Now, using submodularity, we get that that is greater than this. Now, how did we go from the yellow to the green? We got that by the fact that we're conditioning on a larger set. So the set EI minus 1, the set EI minus 1 here, oops, let's use a different color. That guy contains that guy does not contain EI, right? It's just everything up to EI. This guy also doesn't contain EI, but it's a bigger set because we're conditioning on EK. So therefore, by submodularity, it's the left is greater than or equal to the right, which then by definition gives us what's going to be the red. The red. I don't know if you like these color schemes, but there's the red bit over there, just by definition, which we know since it's a polymatroid function, we're assuming everything's a polymatroid function, this is going to be greater than or equal to 0. And so therefore, when we look at this part here and 0, we've got that the whole thing is equal. So f of EK is equal to f of EK minus EI. So we've got that guy, and we've got this guy. Those two things together that are highlighted in yellow right now basically mean that we've also got tightness when we remove EI from EK. So in other words, this is also tight. So in other words, that's tight. And then we can keep doing that. So for EI was any arbitrary member that was not in the support of X, that had that 0 value, right? So we just keep doing that, remove all of the 0 valued elements, and then eventually we get to the point where we're intersecting with the support. Anything that's in the support we can't remove, right? So then, therefore, that an EK is basically as big as we want, and so therefore, support is a tight set. When X is extremal, critical, X is extremal. So that immediately then gives us that support is a subset or equal to SAT, because SAT is the biggest tight set. When X is extremal, supp is less than or equal to SAT. Now, I have a bunch of slides that hopefully will give you some intuition about this stuff. Like, we're going to talk about support and SAT and all these things, and we're going to try to geometrize everything by looking at instances of examples of polymatroids in 2 and 3D. And raise your hand also. I have a little bit of a treat for you, I think. Raise your hand if you like information theory. Okay, a good 43.6% of you, I think. And 43.68% of you, right? So that reveals the number of people in the room, by the way, because of the denominator. So what was I going to say? Oh yeah, so who likes Venn diagrams in information theory? Does anyone like Venn diagrams? Raise your hand. Come on, let's see some confidence here in Venn diagrams. I like Venn diagrams. Okay, so for those of you who like Venn diagrams, there's a little bit of a treat coming up in store. So the question we want to first ask before we get to this treat, which now I'm sure you're agonizingly awaiting for, can or is it necessarily equal to sat? Basically, all we said was sat's bigger than sup. And indeed, it's not going to be the case that it's always equal. And in fact, what's interesting about it is that it really depends on the dependence of the function. And in fact, suppose we take two sets, x and y, right? And then let's say that f of x is equal to f of y is equal to f of x union y. So in some sense, this basically means that x and y are perfectly dependent, if you will. In other words, like the conditional submodular valuation of y given x is 0. So that's like perfectly curved or perfectly dependent or whatever you want to call it. Now suppose we take a particular x that's non-zero at x, but it's 0 everywhere else, and so therefore its valuation on y, which we're assuming to be disjoint, right? So this is x and y disjoint. Don't forget about that. So that means that x of y is equal to 0 as well. Okay. So then the support of x, since the x is only the non-zero value, is equal to x. That's actually, you can't really deduce that, but let's just say that the support of x is equal to x. So in other words, every element of x of vector x at set x is strictly positive. So it's just assert this. I should say this. Assert. Okay, and let's also just assert that x is tight. So what we want to do is come up with an example where sup is strictly less than sat. Okay, sup is a strict subset of sat. So that means sat is the union of all x-tight sets. And so now we've got x of x union y, which is equal to x of x because y is 0. That's equal to f of x since x is tight at x. But then since we've got perfect dependence, that's equal to f of x union y. Okay? So therefore, x union y is a tight set. And therefore, that sat must be greater than or equal to x union y, since sat is the greatest one. And so therefore, that means that sat is greater than or equal to sup. Or sat, in this particular case, is strictly greater than sup. Sat is strictly greater than sup. Okay. And in general, we've got this relationship. It's not like they're equal, of course. Now, the other thing to remind ourselves, to get back to matroids, is that, remember we said that sat was kind of like span or closure of a matroid. So by saying sat is greater than or equal to sup, it's kind of like saying span of A is greater than or equal to A, or as a superset of A. So this set inequality is analogous to this set inequality. Now in the modular case, whenever you have, remember in the modular case, what do all of the polymatroids look like? They all look like squares or hyper rectangles. So in the modular case, they're all the same. If you're at an extreme point, you're also saturated, and vice versa. So the really interesting thing comes about when you have a polymatroid, or when you have a matroid, at least. Okay, so here's again a summary. This is exactly the same slide as what we saw before, except now we've added this property of sat. Now, so we've got sup, which is a subset or equal to sat. Why is this true? Why is dep a subset or equal to sat? Why is that second inequality true?
The part of the same lattice.
Sorry?
The part of the same lattice and set has all the sets. So
They're part of the same lattice, right?
it has to be part of.
That's right. Sat is the maximal x-tight set. Dep is the minimal E-containing x-tight set. Right? D is the elements that are necessary for x-tightness, the n-tight set. Remember, dep is n-tight. And so therefore, if you don't contain, and E is presumably a part of sat, right? So dep of x of E, where E is in sat, is going to be in sat because you can't, that sat includes all possible E's. Okay, so here's an example of some polymatroids. And this is where we're getting close to these are all going to be nice geometric examples that hopefully will strengthen your intuition with regard to all these equations we've been throwing at you. So, first of all, it's a polymatroid in 3D. polymatroid in 3D. It's kind of a weird one because, first of all, we're saying that there's, in some sense, perfect independence between E2, E3, and E1. So E2, E3 is like this axis. There's E3 here, and there's E2. And then E1 is this axis, right? And this is the 0 element over here. Right, so 0, 0, comma 0, 0, 0, 0 is way down there in that corner. So I'm not going to mark it anymore. I'll just put a little gray 0 here just to indicate it that it's 0, okay? So you can see, first of all, when you look at this first face, that there's perfect independence, all of this stuff here. It's a square, right? If you just look at the E1, E2 axis, it's a square, which is essentially what we said corresponded to perfect independence. And then secondly, this face here is also a square. That corresponds to the E1, E3 axis, right? So in both of those cases, when we project down onto those two-dimensional faces, we have independence. But if we look at, say, the E1, E2 axis, we're not saying that they're independent. And so if we look at, like, say, this face here, I don't know if this is 3D. If you're getting the 3D here, I hope you are. But that face, there is a dependence because we've got this, 45-degree line here, which is truncating, negative 45-degree line, which is truncating that face. And so you've got, in some sense, you've got this cube, and we've got this hyperplane slicing off a face of the cube, or a chunk of the cube. Right, this whole bit here is being sliced away. All right, so everybody get what's happening? Now, it's kind of a strange one because, first of all, let's look at some examples. So let's say point X is extreme, right? And f of x, y, x of x is tight at x2, x3. So this is the definition of tight. Why is it tight? Because this is the line here, this negative 45-degree line. That's the line that says f of x2, x3, or E2, E3, I'm saying x here. F of E2, E3, that's the constraining line there. And at that point, where x is, it's equal to exactly that value. So therefore, it's tight. But then if we look at x evaluated at x1, x2, x3. Okay, so x of x1, x of E1, I keep saying x1 when I mean E1. X of E1 is equal to 0. Right? Because remember, when we're at this point here, we're not extended in this direction at all, so therefore it's 0. So that means that x of E1, E2, E3 is equal to x of E2, E3. But on the other hand, f of E1, E2, E3 is separable on these two subsets on which it's independent. So that's equal to f of E1 plus f of E2, E3. And we can see just from the picture that f of E1 is not 0. And so therefore, we have this strict inequality here. So this therefore means that the supp of x, which is equal to the sat, is equal to x2, x3. Right? Supp of the non-zero elements, sat is the biggest set of elements. Because anything bigger than x2, x3 is not tight for this point x. Right? Everybody see that? Now, we can actually cluster the ground elements. So let's take, in some sense, a new ground set, which is E1, and a new element, which is E2, 3. So we're sort of clustering these elements. So that basically means that E1 and E2, 3 are independent. And we can define a new submodular function, f prime, where f prime of E1 is equal to f of E1, and f prime of E23 is equal to f of E2, E3. And what that essentially does is it sort of slices the polytope this way. And you can see, maybe geometrically, maybe, I don't know, maybe this is a better dimension to look at. This is just a rotated version of the same thing. I always do these in two different rotations just so you can see them. But you can see that that's a square or rectangle, right? And so along those dimensions, as you'd expect, when you take that slice, which corresponds to this projection or this grouping of the submodular function, we get a new submodular polytope, which is a rectangle, corresponding to the fact that there's no, quote, dependence between element E1 and element E23. Okay. Now, let's go back to the polytope and look at element y, which is right here, or sorry, vector y. So y is now here. So sat now of y is the ground set. It's equal to E1, E2, and E3. Why is that? Well, sat of x, right, those are the directions that we are saturated in, right? We can't move any farther. But on the other hand, from x, we could move in the E1 direction. But once we've moved as far as possible in the E1 direction, we get to y from x, and we can't move any farther. We can't move up, we can't move to the right, we can't move to the left, or whatever. Sorry, those are not directions. We can't move this direction, we can't move this direction, and we can't move that direction. Whatever permutation of up, down, left, right, forward, backward you prefer to name those axes. Now, what does that mean? So dep, what is dep? Okay, so remember, dep at a particular vector y evaluated E1. Those are the directions we have to move if we want to move further in the direction of E1. But dep of E1, oh, actually, hold on. We forgot all about this other bit. I want to do this. I want to do this part up here first. I'm doing the second line. So let's do this line first. Let's go back to x here. Okay. And dep of x and E1 is not defined because E1 is not in sat. Because dep of a vector and then the element is defined only for those elements that are saturated. But on the other hand, dep of x of E2 is equal to E3 because if we want to move further in the E2 direction, we can do that as long as we're willing to move negatively in the E3 direction, right? But dep of x of E3, if we want to move further in the E3 direction, which would be up, we can't. So there's no other direction that we can move. So we have these three different possible valuations of dep, either undefined, a subset, or the empty set. Okay. Now, getting back to y now, which is the second line down here, when we look at dep y of E1, well, E1 we can't move any further in that direction, right? So therefore it's the empty set. Dep of E2 is equal to E3 again. We can still move that direction if we want to do that, and we can't move in this direction. So dep y of E3 is equal to the empty set. Okay, so basically what it's saying is that for either x and y, we can move in the E2 direction if we're willing to move negatively in the E3 direction, but that's about it. Okay. Is this a duplicate slide? This looks like it's a duplicate slide. See any difference? I don't see any difference. Okay, that's a difference. Okay, so here's now essentially another look at it in two dimensions, which I think offers some intuition that I think is really, really cool. So we have, in some sense, we've been calling these dependents with quotes in it. And the reason why I use the dependents is because I'm sort of generalizing entropy. And something that I think I said at the beginning of the class, which is that polymatroid functions really give us essentially a form of combinatorial independence. It's a generalized entropy. It's not dependence from a statistical perspective in the sense that you have random variables and you measure the dependence between them, but it's dependence from a combinatorial perspective in the same sense as a matroid for a matrix matroid represents linear dependence. We still use the word dependence to to express concepts about items, which in that case are vectors, saying whether or not they're redundant. A vector is redundant if it's expressible as a linear combination of a bunch of other vectors. It's dependent. In an entropic sense, your random variable is dependent if it's the case that it's a deterministic function of a bunch of other random variables, or equivalently, if its conditional entropy is equal to 0. So here we're talking about combinatorial dependence. Basically, given any polymatroid function, we're representing these items, whatever these items are. These are ground elements, but we're representing these items and how they relate to each other, how they're dependent with respect to each other, as given by the polymatroid function. And so what I'm claiming here is that these in 2D, the polymatroid, or in ND, the polymatroid as well, but here we can kind of visualize it. In 2D, the polymatroid gives us an expression of dependence, of various forms of dependence. So let's look at these in detail. So this is the square or the rectangle, and this corresponds to perfect independence or perfect irredundancy, right? It's basically saying that E1 is independent of E2. And why is E1 independent of E2? Because this basically says that f of E1 and E2 is equal to f of E1 plus f of E2. Right? We have perfect additivity between E1 and E2. Okay, the second one, case B, is perfect redundancy. So the slope is negative 45 degrees. Right? So the slope being negative 45 degrees insists upon that we have this. F of E1 is equal to f of E2, which is equal to f of E1, E2. So in the matroid case, it's either case A or B. In the matroid and the polycope, either we have perfect independence or perfect dependence, meaning once you're in the span of some set, nothing is going to get you out of it, right? So, or I should say, there's no partial information in a matroid rank function. You either have a unit increment or not. Now, in this case with a polymatroid, it's not necessarily saying that you have a unit increment. I mean, nothing insists upon f of E1 being 1 as the matroid rank function would. But it really doesn't, it's no different, right? Whether it's valued 1 or whether it's valued pi or some other value, it doesn't matter. It's just some evaluated increment. Okay. Now, where polymatroids really generalize is case C. Now, case C is kind of interesting because it's not yet the most general case. But case C says, first of all, that f of E1 is equal to f of E1, E2, right? That's again based on the, and therefore, but just geometrically, we have f of E2 is strictly less than f of E1. And so this is like basically sort of asymmetric dependence. This is basically saying that E2 is a deterministic function of E1. Why? Well, for exactly this reason, because we have that f of E2 is strictly less than f of E1. And if this was, say, for example, entropy, you could have like E be a random variable, E1 being a random variable. E2 could also be a random variable, but it's some deterministic function of E1. And let's say that, for example, the random variable E1 has 10 values, and the random variable of E2 has 2 values. So it's still random, but its entropy is upper bounded by the fact that it has only 2 values, cardinality of 2. So its maximum entropy, for example, is log of 2. Whereas the maximum entropy of E1 is log of 10. But in general, I mean, even if they're not at their maximum entropy values, you can see that by taking deterministic functions of random variables, you can create other random variables that have entropy smaller. So this is exactly the situation we're in here, but now in the more general polymatroidal case. Okay. And then the last case is D. And D is just the symmetric version of C. So in some sense, we've already covered it. Here it's basically saying that E1 is a deterministic function of E2. Okay. Now we have, getting back to sat and sup, we can see points where sup is less than sat. So for example, let's take this point here, right? This is the point f of E1, comma 0. And so sup, the non-zero elements is just going to be E1. But because of this stream of equalities that I said last time we were going to see over and over again. And we've already seen it today like 3 or 4 times. We saw it last time maybe twice. And here we are seeing it again, but slightly different forms. But basically, this is x of E1, E2 is also, E1, E2 is also tight at x. And that's, again, essentially because of this set of inequalities. So therefore, sat in this case is equal to E1, E2, which is strictly greater than sup. And case D is exactly analogous for this other point up here. Right. Okay, so now here's sort of the most general case, right? Now the most general case is basically saying, okay, well, f of E1, E2 is strictly less than f of E1 plus f of E2, right? So that basically means that that it's not additive at E1 and E2. That, in other words, the two things are not independent. But you know, we had that equality even here in this case, right? So, like in this case, like in case C and case D, we still have. Let's see where can I write this? 1 second. I'll write it here. We still have in this case that's a f of E1 plus f of E2. Is that going to be greater than or equal to f of E1 comma E2? Sanity check. Sometimes I randomly ask you a question. So what's the inequality here? So is the yellow greater than or less than the green? How about I zoom in? So you can't say that you can't see it. Well, what is f of E1? Is f of E1 greater than or less than or equal to f of E1 comma E2? Remember, the lines are always negative 45 degrees. You can just see this just from looking at this plot. It's a negative 45 degree line, right? This guy's negative 45 degrees. Anyone? This is greater than. What about in this case? Let's zoom in here. So f of E1 plus f of E2 versus f of E1, E2. Is the yellow greater than or less than the green? Raise your hand if you are not sure of the answer. Raise your hand if you know the answer and you're just not telling me. Raise your hand if you know the answer. Okay, so why are you not telling me? Everybody knows the answer and nobody's saying anything. Okay.
Can you, sorry, I know like the answer is symmetry, but the intuition just isn't.
In terms of why that's true from the figure, or or what does it mean, or like?
I guess, but how does the figure imply?
Okay. So this line, let's do case C for a minute, okay? So this line here, thank you for asking that. You're very brave. It takes a brave soul to ask a question. So it's frightening being on YouTube. I wouldn't be able to do this when I was your age. Definitely not. It's only what happens. See, wisdom basically is identical to not caring. That's what wisdom is. And when you get old, you stop. They say, "Oh, you're so wise," and what you really realize is when you get old, it's that you don't care anymore. So So this line, does everybody agree with me, or the one brave soul who asked the question, do you agree with me that that's a negative 45 degree line? Okay. So negative 45 degree line. So basically means that this point down here, which I'm going to highlight in beautiful magenta, this point and this point here have the same valuation. For anytime you have a negative 45 degree line, the x and the y axis intercepts are the same value, right? Which mean that this guy, f is less, f of E2 has got to be strictly less than f of E1, right? This means that f of E2 is strictly less than f of E1, just geometrically, right? Now, on the other hand, that yellow line, remember we're defining the basis. This is basically, this is x1 plus x2 is equal to f of E1 and E2. So this, which I'm going to extend this yellow line here. That basically corresponds precisely to this yellow line, right? That's just x1 plus x2 is equal to f. That value, f of E1, E2 is just some value, and that's the equation of that line.
Where any point on that line is equal to some two vectors x1 plus x2.
That's right. x1 plus x2 is equal to f of E1 plus E2. Right? And the line itself goes off forever in both directions, but we're only concerning ourselves with the positive ortho right now because we're only dealing with polymatroid functions. And so therefore, the only part of the line that we care about is the thick yellow line, in which point that value f of E1 and E2, at this bottom magenta point, down here, this guy, this is where you really need a pointer, that bottom magenta point, the value f of E1 has to be equal to f of E1, E2, right? Because that's the coordinate. X is equal to f of E1, y is equal to 0. Right? So this point here, its coordinate is f of E1, comma 0. Right? But that basically must mean that implies, I'll write it up here now, that f of E1 is equal to f of E1, comma E2. Okay? So f of E1 is equal to f of E1, comma E2. So you've got, let's highlight that. That's a critical guy. You've got this guy. Let's use a different color since I like colors. This one. And we also have this one. So f of E1 is equal to f of E1, comma E2, whereas f of E2 is less than f of E1. So therefore, that must mean that this equation is true. This guy. Everybody got it now? Okay. Yep.
Shouldn't be large or equal. Like
We're basing it just on this picture. Okay, so in this picture, it's strictly larger, and the reason why is because of this distance, right? This distance here, that's meant to be greater than 0 strictly. In general, it's greater than or equal to, but in this, we're just talking about this particular picture here. Okay, and similarly with this particular picture on the right. So on the right-hand side, it's strictly greater than as well. Again, because of this delta here.
I'm still a little confused, but the inequality should go the other way.
First of all, when it's a submodular function, that's one of the inequalities that's always true. That the sum of the singleton values is always greater than or equal to the sum of the set. Okay? That first of all, for any submodular function, even non-polymatroidal functions, that's true. Here what we're saying is that for this particular polytope, if this is the polytope, in case C, we have its strictness. And just by looking at, you can just reason by that geometrically. Right. Now, so in other words, in general, we have this with non-strictness for any submodular function. But what I'm saying is, in this particular picture, we still have that f of e1 comma e2 is less than f of e1 plus f of e2, which we did have in the other one. But now we have these two other inequalities. We have this one. We have f of e1 is strictly less than f of e1 comma e2. And why is that? Again, let's use this yellow line trick. We can extend the yellow line down here, extend the yellow line up here. Well, that's not a very good extension. Let's do it again. I guess if I was writing this all on the blackboard, it would be really messy anyway, wouldn't it? So this way, I'll just write it much more neatly. So we extend the yellow line. And what is this valuation down here? So this valuation here is just going to be, this is going to be f, this valuation at this point is f of e1, e2. At this point, this black point which I'm drawing. And this other black point up here, that valuation here is also f of e1 comma e2, right? Which we're saying in each case is strictly greater. So we have strictly greater in this case down here, and strictly greater in this case up here. Okay. The other strictly greater corresponded to this inequality, this strict inequality. So this really corresponds to, I mean, if you're thinking about this as an entropic, if you like entropy in random variables, which we tend to like in machine learning, we have some random variable z. Z is any arbitrary random variables, and you have two separate deterministic functions, say h1 and h2. Those are two deterministic functions of z, the random variable, which gives us two new random variables, e1 and e2. But it's not a trivial function in the sense that e1 and e2 are still random. It's not like e1, the entropy of e1 is 0. But it is the case that the entropy of e1 is less than the entropy of z, and the entropy of e2 is also less than the entropy of z. And so we have this guy down here. But it's not the case that the sum, obviously the sum of the two things can't have entropy less than that of z, right? Well, actually, that's not true. But in this particular case, we have that, what I just said was wrong, but in this particular case, we have h of e1 plus h of e2 is greater than h of z, corresponding to this polytope. Okay, so this polytope then allows us to visualize properties of, if we're in an information theoretic setting, if we're talking about random variables, it allows us to reason about properties of random variables. And in fact, the condition goes even further. I mean, so everyone is familiar with, presumably, Venn diagrams. So here we have all these Venn diagrams, and so what I'm doing is I'm putting a corresponding figure between the polytope and the corresponding Venn diagrams that you often use in information theory. So here's the Venn diagrams. So oftentimes in information information theory, you have pictures that say, okay, this is the entropy of x, and this is the entropy of y, and the entropy of x and y is everything, and this guy is equal to maybe, the middle one is the mutual information between x and y, and this is the entropy of x given y, and this is the entropy of y given x. And you use Venn diagrams for that. Right? And what I'm claiming is that this polytope up here shows you exactly the same thing. Right? This polytope corresponds to this figure. When you do have an intersection, when the mutual information is strictly greater than 0. This Venn diagram corresponds to the case when the variables are not independent, but the variables neither are fully dependent either, meaning one isn't a deterministic function of the other. And that's sort of the most general polytope. But we have these other cases, like this case when you've got a modular function, which also corresponds to everything being independent. And so if we were to actually write a Venn diagram for that, you just have two non-intersecting circles. The mutual information between E1 and E2 is 0 if this is an entropy case. Or you have additivity. Additivity is independence, modularity. You can break things down into its component parts. In fact, modular, the term modular corresponds precisely to that. That it's like you have modular components, like it's like you have these different components which are somewhat sort of separate and independent, and they can sort of, you can manufacture them, and the whole modular term corresponds to a modular function for that reason. But then this other figure we have, the perfect dependence, which is the matroid dependence case, corresponds to the two Venn circles are right on top of each other. So the idea is that the green is the intersection, and dark green is the intersection. And you can see that we've got a dark green circle, which is really the two circles, the blue and this light green on top of each other, which corresponds to this triangle. This guy here, where E2 is a deterministic function of E1, corresponds to this Venn diagram, where the E2 information Venn diagram is strictly contained within the larger one, within the light green one. So dark green is contained in the light green. And then this other one is the opposite, where dark green is contained in the blue. But then here they are all together. So, but now it turns out that the polytopes actually say more than the Venn diagrams, unless you're very careful and you say that the measure, the area corresponds to some sort of measure. But basically, like if you take this particular polytope, I mean, whatever this value is, that corresponds to the value of the submodular function on E1. And whatever this is, this corresponds to the value on this one. So you could, for example, like talk about the difference between, say, that polytope and maybe something that looks really like this versus something that looks like this. You could have very different looking polytopes. In this case, let's do the yellow one first. In this case, it's basically saying that f of E1 is much larger than f of E2. Whereas in this case, it's the red one, saying that f of E2 is much larger than f of E1. And in both cases, there's some dependence. But it in some sense gets even more interesting than that, because you can actually take this top part of the polytope, like this green part down here. That actually means something, that little green bit. That sort of corresponds to the degree of dependence. So remember, we defined early on this sort of information function. I of f of E1, E2 is equal to the difference between the modular and the submodular evaluation. So this is like this, if this is the entropy function, this is equal to the mutual information. But what if we were to then compute the area of this lower triangle, of this dark green triangle? What if we compute the area of this thing? So how do we do that? Well, let's just use geometry, just very simple geometry. And it's 1/2 times the width times the height of that square, right? So you can see the triangle is half of the area. So when we do that, this is really just 1/2 of this quantity squared. And we get that quantity, it's f of E1 plus f of E2 minus f of E1 comma E2. That's from the definition of the conditional submodularity. So therefore, the area of the triangle is equal to 1/2 of the combinatorial independence function squared. So it's like that little shape. And this is true in general. Like when you take an n-dimensional polytope, that bit, which is lopped off of the base polytope, corresponds to the degree of the dependence amongst the random variables, or amongst the data items, or ground elements, or whatever you'd like to call them. So the polytope reveals something very, very deep about the relationship between the items that you're measuring with this submodular function. Okay, so let's do a couple more examples, fun examples. Here's an example that is symmetric in a particular way. It's symmetric about, in some sense, all axes. But let's define it in a very asymmetric way first, and see if folks recognize this. This is actually an example that comes about from Bayesian networks, believe it or not, but you probably don't recognize it at first. Raise your hand if you know what a Bayesian network is. Okay, so for those machine learning graphical modelists in the world, this will be familiar once we reveal how it's familiar. But let's say that we've got perfect independence between E2 and E3. Okay, so that basically means that we've got additivity. E2 and E3, we're additive at E2 and E3. But we've got perfect dependence between the group E2, E3, and E1. So that basically means that the valuation at at the set, E1, E2, E3 is just equal to the valuation at E1, E2. Okay. Now, looking at the polytope for this, so if we march along, let's see, starting at 0, I have to get these axes right. If we march along E1 first, so starting at 0, so 0 is in the center. Maybe let's zoom in a little bit so you guys can see it better. So we march along E1 first and E2. So there's an extremal point. And that face is then defined by x of a is less than or equal to f of a for all a subset, right? But what we're saying is that at this point we can't move up, right? We're stuck. We can't move once we're at that extreme point, we cannot move up in the positive E3 direction. So we're stuck. And just intuitively, what this means is that f of E3 given E1, comma E2 is equal to 0. Or in other words, that's saying that f of E1, comma E2 is equal to f of E1, comma E2, comma E3. And I shouldn't have done that in yellow, but actually, there's a way out of this dilemma without having to rewrite it, I think. I think I can do this. Let's see if this works. Amazing. The power of the iPad is revealed. The only thing more powerful than submodular functions is an iPad. It's Steve Jobs. Steve Jobs. He was submodular, by the way. So there we are, right? So we've got this. Just again, thinking at it geometrically, we've got this equality. Okay. Now, how does this come about, and what does this have to do with Bayesian networks? So basically, we've got. Let's take a Bayesian network with a V structure. Do I have a picture of this later? Yeah. So I can't remember if I've got a picture of this, but let's say we've got E2 and E3 and E1. These are now, think of this as random variables. So E2 and E3 is a V structure, meaning that E2 and E3 are independent, say, binary random variables, and E1 is a E1 has as parents E2 and E3, and E1 is the XOR of E2 and E3, right? So they're pairwise independent, right? They're pairwise independent, but any two is fully determines the remainder. Now, how do we get pairwise independence from this figure? Look at all the faces. Like, that's a square there, right? This is a square here. And this is a square down here. So all pairs are independent. But any triple, as soon as you have any two of them, like go to any extreme point. There's an extreme point. We can't move in the E2 direction once we're here. We're stuck. Or once we're here, we can't move in the E1 direction. And we saw the one before here. We can't move in this direction. So there's this symmetry, right? As soon as you've got two, you're stuck. You can't move in any other direction. Now, what about depth? When we're at that point, when we're at either one of these extreme points, let's say that we're at this point here. Let's call this guy x. So depth of that point, if we want to move, say, in the E3 direction, we could either move in the E2 or the E1 direction. And so basically saying that at that point x, at that polytope, at that polyhedral extreme point, both E1 and E2 are dependent on E3 together. So in some sense, depth is, it's like the dependence function, therefore. Okay, so I think we said all this stuff here. Any questions about this?
Is the V structure E2 and 3.E1 unique, or is that just one? It seems like there's some 3D symmetry.
Exactly. That's exactly the whole point. So in this example, so if in the, I can't remember if I have this thing spelled out. I wanted to do something else, but let me just add a page and and I can't remember if I say this later or not, but so whenever you have this kind of Bayesian network where you have, say, E1 is a function of E2 and E3. So basically we're saying that E2 is independent of E3, and then E2 and E3 are both binary uniform random variables. They're both fair coin flips. And then E1 is equal to E2 XOR E3. So that structure is identical to, say, if we do E1, E2, and E3, which is identical to if we do E1, E3, E2, right? Those are identical Markov equivalent Bayesian networks. And those three Markov equivalent Bayesian networks corresponds to this polytope. But now here we're talking not necessarily about statistical independence, we're talking about combinatorial dependence. But the same phenomena exists. You can still represent V structures in some sense using polymatroidal constructs. Now V structures are kind of neat because if you were to, say, take my graphical models class, you would learn that V structures are exactly the things that can be represented exactly by Bayesian networks that can't be by Markov random fields. But still, with these combinatorial dependent structures, we can still represent V structures. So they're still expressible within the polyhedral structure. So again, I mean, the other thing I wanted to show you was this. Like if you look at, this, let's use yellow again. So if you go diagonal over here, then across here, and across there, and across there, we get essentially this polytope, remember? Where E1 is a deterministic function of E2 and E3. But in this particular case, this is true for any permutation. So the way that we've notated it here is, let's say that sigma is any permutation. And then we group them according to the first two items of the permutation and then the last items of the permutation. If we take any grouping, the corresponding slice of this polytope is going to look like this. And one way would be to do this yellow one that I did. Another way would be to do, hopefully I won't screw this up, a green one like this. And let's use red. And the third one would be to do this one. Is that right? I think so. Can't really see it very well. But any of those permutations gives you the red, green, or the yellow slicing of the polytope. All of which look like this stuff down here. Now the other thing to note is that for some of the extreme points, there are multiple orders that can generate the same extreme point. So like, let's consider this point here. I can never remember. 1, 1, 1, 0. So let's do 1, 1, 0. So this point here is 1, 1, 0. Okay. So how do we get that point? Well, we could get it either from going this direction. We could do E1, E2, and E3, which doesn't move us anywhere, right? Because E3 given E1 E2 is equal to 0, as we saw. Or we could get it with E2, E2, E1, and E3. Again, because the E3 direction given E1 and E2 is equal to 0. So both of these orders generates that same extreme point, 1, 1, 0. And in general, that's true. Can you imagine a polytope for which every extreme point has a unique ordering? What must be true of the submodular function? So what is true of this submodular function? What's true is that the gain f of E3 given E1, E2 is equal to 0. So it basically says that you choose some order, and at some point you get into a situation where when you condition on some history, you get a gain of 0. Right? So that basically means that you don't move in that direction. That's actually, there's a concept called the curvature of the submodular function. And this is exactly, these gains of 0 is one of the things that actually makes submodular function minimization more combinatorially difficult. whenever it's the case that the gains are strictly positive, then each extreme point is going to be unique. Or uniquely generated by, I should say, each extreme point is going to be generated by unique ordering of the elements. That's really what I want to say. So this is this Bayesian network structure. I think I already had this. I sort of wrote this down. So let's just skip over that. Okay, so this stuff I think I already said. Basically, I just want to say SAT's greater than or equal to sup. And if we take any element out of sup, obviously this is true. But, oh yeah, here's what we want to say. So basically, the main point, which I have a few lines of reasoning here, but I just don't have time to go over it. So if we take some direction that's in SAT but not in sup, so it corresponds to a zero element direction. So we're at an extreme point, but there's a zero valuation, but still saturated. Then we've got this gain of zero, right? So this is this gain of zero. F of EI given sup of x is equal to 0. And that's exactly the condition that we saw. So it's the SAT and the sup. If we have SAT and sup queries, we can sort of understand all of that kind of stuff. And so here's just, all that stuff is there is just the proof of this. But basically, here's the critical thing. For any A, which is a subset of SAT except for sup, we've got that F of A given sup is 0. The gain is 0 for any A. Okay. The argument in this stuff above is very similar to what we've already seen. So this is now all for polymatroid functions. For modular functions, they're the same, as we said. And then for x, when we're not extremal, then the relationships don't really make sense. I mean, this is all for extremal points. But as you'll see, it's really the extremal points, or near the extremal points, or on the base. That's really what we care about, as you'll see for algorithms. So here's a polytope, actually. I asked what would be an example of a polytope where every different order generates a unique extreme point. Well, it's a very simple submodular function. It's the square root of cardinality. It's one of the simplest submodular functions. It's actually one of the ones that has traditionally been used as a test submodular function. But it's actually a relatively simple one. And first of all, it's got a gain that's always strictly positive, right? Because every time you add an element, the square root never saturates. The square root never gets to 0. So therefore, it's always strictly positive. And you can see that there's the symmetry about this polytope as well, right? But the base is this nice symmetric polygon, right? This guy. This is the base. Okay. So the critical thing is that any extremal point based on a prefix order, so we choose some order here, and then the sup in this particular case is going to be equal to the SAT. Why? Because if we take any particular extreme point, which need not be on the base, like we might take a point that, say, lives here, say, or even here, or anywhere, any of these extreme points, what's going to happen is that there will be additional directions we can add that don't increase the vector, right? Because the vector is going to be 0 at this point, because sup is not everywhere. But every time we add a point to the submodular evaluation, we're going to strictly increase it. There's no such E that has this equality here, because the gain is always strictly positive. Okay, so therefore, we have that the largest tight point is the same as all of the points that are non-zero, or sup and SAT are the same. Okay, and so there's an example of that. Okay, so this is maybe a good enough time. There's a couple of really other interesting facts about the base polytope that I want to mention to you, but maybe we should take a very, very short break and come back and reveal these great theorems to you. And then maybe, if we're lucky, get onto the min-norm point algorithm. So, talk to you soon. Okay, so here's a nice theorem that that's very revealing to everybody. That basically gives us something that it tells us the dimensionality of the base polytope. Basically, saying that the dimensionality of the base, like we saw in one case, like for example in this V structure generalization, polymatroidal V structure case, we saw that. Sorry, I take that back. In the case of when we said that E1 and E2 were independent of E3, we saw one sort of strange-looking polytope. And then in these other cases, we saw that the bases seem to be two-dimensional. So what this theorem says is that the dimensionality of the base polytope corresponds precisely to the number of separators of the submodular function. So the number of separators basically means essentially the following: that E1 and E2 up to EK are sort of called separators if it's the case that the submodular function can be written as the sum of submodular functions, each of which is restricted to the corresponding separator. So in some sense, the partition from E1 through EK sort of is such that we are additive across blocks of the partition. And any valuation A is such that we are additive in each block. And so you can sort of think of it as like having k separate submodular functions, one for each of the blocks, right? And you can construct any separable submodular function in this fashion. In fact, in the graph cut case, when we do graph cuts, we kind of do something like this, except that it's not a partition. This, as we know, this construct that I highlighted in red preserves submodularity. It's one of the things we talked about in lecture 2 and 3. But what we want to say here is that if it's the case that the submodular function can be written in this way, and k is maximum, it's the largest such k such that we can write it, then the base polytope, which is defined in this way, has dimension e minus k, the size of e minus k. So in general, it has dimension e minus 1 for a general submodular function. But if it's the case that if there's some form of independence between disjoint AB, then it reduces the dimension of the base. So this means that any point in the base is a convex combination of at most e minus k plus 1 points. And in general, it's saying that the base is itself, in the most general case, at most e minus 1 dimensional. So it can be represented as a convex combination of e points in the base. And this is actually something that's important for many algorithms. So here's an example. This is the example that we saw before. So we saw that E1 was independent of E2 and E3. In other words, the blocks were E1, E2, or sorry, E2, E3, and E1. And so what that means, like you might think, oh, well, here's the base, right? No, that's not the base. The base is just this one-dimensional line. The base is just this bit. This right here. That's the base polytope. It's just this line segment. And here it is again, from a different perspective. We like perspective. Yep.
But the line segment itself is in 2 dimensions, right?
What's that?
The line segment itself, in the bigger scene, is in 2 dimensions, right?
Right.
But still we are saying that the base dimension is only 1.
Well, here, this is, in this particular case, it's a one-dimensional polytope, yeah. And it's just, which is a line segment.
So we are taking that same segment independently of everything else. We're not looking at it in the context of the whole system. The whole system had 3 axes, and if you have only a line segment in the 3-dimensional structure, it will be in 2 dimensions. But because we are saying that the whole base is only 1 dimension, that means we are not even caring about what the original structure of the prototype was. No,
of course we're caring about the original structure. All we're saying is what the theorem states. We're saying exactly what the theorem states, which is that if there is this dependence, if there's this separability, which we said in this polytope, remember we said that there was additivity across A and B, where A and B are these sets. Right? These are the sets, A and B. There's additivity across the set. Basically, it's changed the shape of the polytope. The polytope, in fact, looks like this. And the base polytope, the section of R3, this is the thing that satisfies that equation, corresponds only to that line segment. Whereas more generally, the base, we said, corresponds to something much more, the base normally corresponds to this bit, right? That's normally the base. Normally the base in that case is this two-dimensional polygon, right? We're in R3, and it's a two-dimensional polygon. It's a segment, in some sense, a section of a hyperplane. But in this particular case, there's no dependence. When you take the square root of the cardinality function, nothing is independent of anything. I mean, that really gets at the heart of the power of submodular functions, which is that and why they're sort of non-graphical. Because in a graphical model, you're saying all of the simple aspect of the structure, all of the constructs that make graphical models simple is the fact that you have decomposability. You've got the ability to distribute sums inside of products. You've got factorization. And the graph basically expresses factorization properties from probability distributions. A submodular function, first of all, is more general than a graphical model, but for the purposes of this particular discussion, a submodular function has a very different form of simplification. It doesn't say that you need to have factorization or decomposability. You don't need to have additivity. Because decomposability in a graphical model is the same as additivity. When you take the log of something that factors, it sums. It's additive over the terms in the log. In this particular case, in the submodular function, you've got a very simple, completely non-decomposable submodular function, square root of cardinality A, right? Nothing is additive. You can't say that f of A union B is equal to f of A plus f of B for any AB when the submodular function is the square root of cardinality. It just doesn't separate because of the nonlinearity of the square root. It's still restricted. It's a very simple form of non-decomposability, but it is nonetheless. And so therefore, in some sense, it's like the antithesis of a graphical model. That's why I sometimes say that submodular functions are like anti-graphical models, because they're not graphical necessarily. Although we still like to use pictures, and I think that the reason why we're spending all this time on the polytope is that this polytope, at least, I mean, we obviously can't visualize in more than 3 dimensions, unfortunately, but this polytope, at least up to 3 dimensions, helps us to visualize some of the interesting properties that submodular functions have and what they can do. And also leads to good algorithms, as we will see. So that's basically what this theorem is stating. You might ask, does the base exist? I mean, there's a trivial proof that the base does exist. So why do we know that this thing really exists? I mean, the greedy algorithm just gives us that. Because when we choose the greedy order, we just choose the order and we start generating x. So we saw before that we have that x is in the polytope and that it's an extreme point in the polytope. And then lastly, if you evaluate x at the ground set, we're going to be equal to e. So then we know that there has to, when we have a submodular function, be at least one point that comprises the base polytope. The base polytope cannot be empty for a submodular function. Okay. Another thing we want to say is that we can generate a particularly important point that's in the base. We can generate a point in the base that's tight at A. In other words, we can generate a point in the A. Let's say that AX, let's not use green, but let's say that X is in the base, and also that X of A is equal to F of A. We might want the point. Now, why would we care about such a point? Because when we're in the point, we first of all know that since X is in the base, which is we have that X of B is less than or equal to F of B. So what does this mean? It means that we have essentially a modular lower bound that's tight at a particular point A, just by generating points inside of the polytope, and then that's tight. So think of what this is. This is like a subgradient, right? I mean, for example, whenever we have a convex function and we take a subgradient or a derivative, that's like a linear lower bound that's tight at that point. Any vector inside of the polytope, PF, is going to be a modular lower bound But here's one that's tight at a point, meaning that it's tight at A. And so that can be treated as a subgradient, which leads us to possibilities for doing things like first-order gradient-based optimization of submodular functions, which in fact has been a big part of my own research for the past couple of years. I was looking at first-order methods for submodular problems. Now, how do we get this? How do we get this? It turns out to be extraordinarily easy, given the tools that we now know. We choose the ordering, but we choose the ordering in such a way that, let's say that A is of size k. We choose the ordering so that E sub k is equal to A. Other than that, it doesn't matter. Any ordering suffices. Now, how many of them are there? There's quite a few possible orderings, so you have a lot of choice. But there's a lot of subgradients. It just basically means that all of those points are subgradients. And so you generate x via the greedy using that particular order. And so here it gives you the valuation. So we basically just do these conditional gains. Right? And then what we know, just by the process that we've already got, that when we evaluate that x that we've generated according to the greedy order at A, that's equal to E sub k, but E sub k, we've chosen that to be A. So we're tight, therefore, at A. But since we also know that we're a member of the polytope, because we proved that a couple of lectures ago, we know that we're a lower bound everywhere else, modular lower bound. And also, we know that if we keep going till the end, we've got x is in the base, right? Because we know that x of E is equal to f of E. So therefore, we've got a point in the base. So any point in the base, so you can generate all of these points if we continue them until the ground all the way up for the whole ground set. We get a large number of tight modular lower bounds, tight at A, and that are members of the base polytope. This is the base, right? Now, the other thing that this says, actually, this last thing I want to mention, this says that the base, which is tight at E, right? So this basically says that x of E is equal to f of E, right? And this other set of points that are tight at A is non-empty. So this says something very, very powerful about the base. Let's talk about this in 2 dimensions for a minute. So here's a 2-dimensional polytope. What this is saying is that this base here, let's zoom in a little bit. 2 dimensions is easy to reason. So here's the base, which is in green. And this line, let's do this in dotted yellow, intersect. So equation 15.2 basically says that for any A, the set of points in RE that are tight at A intersect the base. So in words, you can essentially say that the base polytope intersects, if you will, all multi-axis congruent hyperplanes. So in other words, these are the multi-axis congruent hyperplanes, and the base intersects all of them, every single one, including the singleton one. So including x such that f of lowercase e is equal to f of lowercase e for all e. So the base is a really strange shape. In fact, this is a theorem I want to mention. This is sort of saying the same thing, but slightly more powerful. It's saying that every x in the polytope itself is dominated by a y which is in the base. So if you're in the polytope if you're in the polytope P of f, then there's some y which is strictly greater than you at all. Well, I should say not strictly greater than you. There's some y which is not less than you at all points exists that's also in the base. So you only have to go up in all directions or stay the same. And so here's the more formal way of saying that is the following. Let's choose a particular point x in the polytope. And let's say that we're already tight at some point. So meaning like there's some set t which you're tight at. So x of t is equal to f of t. So you're tight there already. And that's sort of like the multi-axis congruent guy. What this is saying is that there's some y in the base where for all of the elements T, all the guys that you're tight at, you keep the same value, so you don't change those directions. But for the other directions, the guys outside of T, you get bigger, say. You can do that because you're not tight, right? Because those are not in the sat. There's a saturation capacity for those points, and you can therefore increase those values. But all you need to do is go up in those directions. So I'm not going to prove this theorem, but I want to make sure everybody understands the theorem. The proof is here. I think that you should look at it offline. But first of all, the statement of the theorem really means that the base polytope is sort of above everything in n dimensions. So here's the proof. We can go through it. It's actually a neat proof. I recommend everybody reading it. It uses the exchange capacity and these tools that we've got. But given that theorem, is this a submodular polytope? We saw this a couple of weeks ago. I have to tell you that I discovered this polytope serendipitously, by accident. Although it turns out to be something else. But the point is this a submodular polytope? So remember, the theorem that says, think geometrically, says that if you're here, you have to be able to go strictly up and hit the base, okay? But the problem is you can't go strictly up. Because the base doesn't go all the way here, right? You have to go sort of up and to the right. So therefore, the base doesn't intersect all multi-axis congruent subspaces in some sense. Right? So therefore, it's not a submodular polytope. And in fact, you can get this by, right, so here's the statement. This base in this polytope doesn't intersect, say, x, such that x of e is equal to f of e, which would be these faces. Right? So like, here's one face, here's one face here. That plane, the one that's intersecting here. Or this plane, the one that's intersecting that guy. Or this plane, the one that's intersecting that guy, right? You can see that the base doesn't intersect any of those guys. So therefore, this is not submodular polytope. You can learn to recognize them geometrically. And it turns out that this is generated by this function, which is this function that we saw before. And it turns out that it's it can't be a concave function over a modular function. So it's not a submodular function. It's a polytope according to some non-submodular function. What about this one? Is this a submodular polytope? I will zoom in and scroll around so you can see it. This is our animation. Move the mouse out of the way. What do you think? It's earthquake. Okay, sorry. Is it a submodular polytope? So where's the base? If there was one, the base would be this point here. And let's take one face. Let's take the hyperplane that's parallel to that guy. So you can see that it doesn't intersect the base because there's this little bit of gap here. You have to sort of go in. So therefore the base, or if that is the base, doesn't intersect all x such that x of e is equal to f of e. Yep.
Why isn't the base still intersect from that point to that?
Well, the only reasonable point for the base would be this guy here, right? Because all these other guys, like this guy's restricting, this is a two-dimensional restriction here, this is a two-dimensional restriction here, this is a two-dimensional restriction here. If this was one, you'd have another plane here, which is just touching at that point, right? So that guy's not restricting anything. If it was the case that we changed it so that that the base, that it looked like something more like this. Meaning it's not that triangle is gone, it's just the yellow thing, then it would be submodular polytope again. Because even though that there's one point of intersection between the base and this face here, that's okay. It's intersecting all of these guys. This guy, this guy, this guy, this guy, this guy, and this guy. Okay. So, everybody see that? Okay.
I have a question.
Yep.
Why are we not considering intersections with the backplanes? Basically, E1, E2, E2, E3, and E1, E3.
You are.
But then it's not intersecting the base, right? Basically, in the
No.
example where we
Which? So this one here.
yeah.
Okay. So you're intersecting. This one you're considering all of them. So think about it. So let's hold on. Let me just put this triangle back. Not erase so drastically. So let's do an example. So x such that x of E1 is equal to f of E1. What's that? That's basically this guy. Right? In other words, this bit here is what that corresponds. We're extending that everywhere. That's what that line is. Are we intersecting the base? Yes. What about another one? Let's do x.
I think it's talking about the non-negative orthant constraint, which is not one that has to do with the function.
We're only talking. These are only polymatroids. We're just talking about polymatroids here. So everything is in the positive orthant. Remember we talked about this. Like when it's a polymatroid, all gains are non-negative. Everything, all of the structure of the submodular function lives in the non-negative orthant. So there's nothing going on in the outside of the positive non-negative orthant in the polymatroidal case.
I think he was just asking about x, y, y, z, and x, z.
Yes, that's what I was about to do. So if we take x of say E1, E2 is equal to f of E1, E2. Which one is that going to be? That's going to be this one. So what face is that? It's going to be this one. Extending it, it's going to be this way. We're intersecting the triangle. Okay. That's x of E1 plus x of E2 is equal to this constant f of E1, E2, which is just this negative 45 degree plane in R3. We're intersecting. So every example, obviously the x of empty set is equal to 0. That's not going to be intersecting. But that's just this point down there at the origin, right? Does that answer your question? Okay. Okay. So this is also not a submodular polytope. Okay. So all right. So we're obviously not going to get to min-norm point today. So let's try to see if we can finish the notion of exchange capacity. So remember the saturation capacity is something that we saw. So for those elements. The saturation capacity were for those elements that are not part of SAT, how much further we can move in those directions while still staying within the polytope. And that we saw was identical to this submodular function, this E-containing submodular function minimization problem. This was known as the saturation capacity associated with X and E. And we also know that matroids have an exchange property, and we saw that there's the fundamental circuit of a matroid. This is all review. We've already seen this before. And then we saw that how dep generalizes the fundamental circuit of a matroid to polymatroids, and how you can define dep. We saw that we can define the fundamental circuit as an exchange. We can say that the fundamental circuit are those elements that if we remove an element and lose independence, we can remove these other elements and regain independence. So those are the things that define the fundamental circuit. And similarly, we saw how dep was basically those elements that if we add some element E, those other elements we can remove, or in other words, if we want to move in a particular positive direction, those are the elements that allow us to move in the particular direction by moving correspondingly in the negative direction. Those are like geometric exchange. But the question is, just like in SAT, for things that are not SAT, there was an amount by which we could move and stay within a polytope. For depth, we don't have an exchange capacity, like how much can we exchange? And that's what the exchange capacity answers for us. It gives us a concept like that. And so for this to make sense, we need to choose, it's all relative to a particular x, which, for all intents and purposes is going to be an extreme point. And we choose a saturated point, and then we choose one of these exchangeable points, E prime. So that's not E. So obviously, otherwise it would be trivial if we chose the same point. And so the question is, if we move, since dep is a subset of sat, right? In any of these directions, E or E prime, we can't move in the positive. We can't move positively in either of those two directions because we'll immediately leave the polytope since we're saturated there, right? And that's what this is saying. And here's an example. Like if this is x, we can neither move in this direction, nor can we move in this direction, or we can't move in this direction, nor can we move in this direction. But in each of those cases, if we want to move in, say, the positive E direction, we can move in the negative E prime direction by going this way, right? This is stuff we've seen before. But the question we want to ask is, how much can we move? Like here we can move this amount, and here we can move this amount. And we want to measure how much. And that's what the exchange capacity buys us, or tells us, I should say. And so we can define it in this fashion, where we say, okay, again, where we're taking E and E prime in a way that makes sense. The exchange capacity corresponds to the maximum value alpha, where alpha is a real value, such that starting at x, we can move positively in the E direction and negatively in the E prime direction and still be inside of the polytope. Okay. So this is identical to essentially saying this. Now, by being inside of the polytope, we basically are saying that, we have to satisfy this inequality for all A. Hopefully this is clear to you. This is basically like treating this whole thing as one vector, then evaluating it as at A. Okay. Now, if it's the case that both or neither E or E prime are in A, then basically the statement becomes vacuous because we're just adding and subtracting alpha. So in order for this to be non-vacuous or meaningful, basically we need to take, let's say, E inside of A. So A contains E, but A does not contain E prime. Okay. And so then we add this so that it actually becomes a meaningful statement. We add these constraints. But then this is identical to just rearrange a couple of terms. We're basically now just putting the x on the other side, which was here. So it's basically saying this vector evaluated A has to be less than or equal to this valuation. But because we said that E prime is not in A, suddenly this part here doesn't matter. Oh, sorry, not the inequality. This part evaluates to 0, right? So that part, we just get rid of it, and it was here, by the way, and now it's gone. It was 0. And then alpha times 1EA, since E is a member of A, just turns into alpha. So it's the maximum value of alpha such that this inequality is true for all subsets of A where we have this condition here. But then that maximum is achieved at this value here, the minimum of the difference. So the minimum of this constrained, it's like this constrained submodular function minimization problem. It's constrained to be E containing, and E prime not containing. And that's still a submodular function. You could define a submodular function where you forcibly include E in the ground set, remove it from the ground set, and forcibly add all valuations to have E, and then just remove E prime from the ground set. That's still unconstrained submodular function minimization. And that's the thing that gives us this value alpha, which is the exchange capacity. So we've done the same kind of tricks that we did for SAT and for depth. We have two definitions, one which is in terms of submodular function minimization, another which is in terms of these geometric movement things. So this is the exchange capacity. So what this means then is that if we take any alpha between 0 and the exchange capacity, we can do this movement. And of course the alpha, for example, would correspond to, if this is a polytope, it would correspond to, say, starting here, and it would correspond to moving a certain degree along, say, the base. And how much do we move? And then the exchange capacity is moving fully from one vertex, from one extreme point to another. Now what's really interesting, and what gets into some really a little bit deeper stuff associated with the base, it turns out that the extreme points of a polymatroid correspond to a partial order. In other words, there's the extreme points themselves constitute a lattice where you can define union or join and meet of extreme points using it's not just the min and max lattice that we saw, for example, for real vectors. In fact, doing that wouldn't even necessarily retain the notion of it being an extreme point. But there are join and meet operators we can define, and in an ordering, which we will talk about in a few lectures, that gives us that lattice. It's this exchange capacity that moves from neighboring points, between neighboring points. If that makes any sense, which probably won't for a while. Okay. Are there any questions about that? Okay, so let's now back up for a minute. Okay, so where are we going here? So we defined all of these tools. We've got the supp, the sat, the dep, the saturation capacity, the exchange capacity. We have hopefully a nice intuition about the submodular polytope right now. And what I want to do is sort of come up with a nice description or sort of a proof of a particular simple characteristic of an algorithm that will give us the minimum of a submodular function. Now, what we're going to use is this theorem that we saw several lectures ago at this point now, which is this min-max theorem, which was proven by Jack Edmonds back in the 60s, which is this vector rank function. Remember the vector rank, which is basically the maximum independent subvector of a given vector x is equal to the min of this submodular function. So this theorem is really critical for proving a given algorithm works for submodular function minimization. This is saying that, for example, if we take x to be 0 here, then we've got the rank of 0. The rank of the 0 vector is equal to the maximum component sum of all y less than or equal to x. So a subvector has to be saying that we're strictly in the negative orthant, right? Because it's saying that y is less than or equal to 0, and you're in the polytope. Now, of course, this only really makes sense when we're talking about the extended polytope. We've been talking about the polymatroidal polytope so far, but here we're specifically talking about the polytope PF, which is equal to all x in RE, such that x of a is less than or equal to f of a. So notice this is no longer necessarily a polytope, or even it's a polyhedron, right? It's not a polytope anymore. It's a polyhedron, and it does not necessarily live in the positive orthant. But remember that it's essentially equivalent to a shifted polytope, because we can take any submodular function and represent it as a polymatroid function minus a modular function. So it's just like taking the polymatroidal polytope that we know and love that lives in the positive orthant and then shifting it down some. So we're subtracting some modular function from it. But it means that it might live somewhere else. Like I've got some pictures of it in a minute, but it might live, say, if these are the axes, it might look something like this. Right? It might be shifted down. The other thing is that the theorem becomes trivial, like when we do have a polymatroid function. So when we have a polymatroid function, what's the minimizer of it? What's f of the empty set? It's a non-negative monotone, non-decreasing submodular function, which is normalized. So therefore, at the empty set is equal to 0. So the right-hand side, we get that the empty set is the solution here. And the left-hand side, we're saying, okay, well, what's the maximum subvector of the 0 vector? It's just 0. And then what's the component sum of the 0 vector? That's going to be 0. So for a polymatroid function, this is still true, but it's just trivial. So this really only becomes interesting when it's the case that f is not a polymatroid function, and where f is really some polymatroid function where it's minus a modular function. And moreover, it necessarily means that these valuations, the 15.6 valuations, are going to be negative, or 0 at most, right? But one thing, the real minimizers are going to be at most 0. Since we're assuming the submodular function is still going to be normalized, and we have a trivial valuation at 0, which is equal to 0. Okay, so here again is the theorem, right? The minimizers of the submodular function. Now consider the following optimization problem. So we're minimizing the squared 2 norm of a vector subject to it being inside of a base. Okay. So remember, B is the base polytope, which we now have, which we've spent time gaining intuition about. We have all these properties of the base. This is just the squared 2 norm. So it's the sum of the squared entries, right? It's the sum of E, x of E, quantity squared. Well, actually, it's written right here, isn't it? So I don't need to write it. And let's say that x prime is the optimal solution, or x star is the optimal solution. So let's just do a couple of pictures, and then we'll break. So here's an example. So the yellow regions are the possible thankfully, we have a back button. Otherwise, I'd be flipping around a lot. But basically, the yellow regions are the possible polyhedrons, right? And the circle corresponds to the contours of the 2 norm, the equal contours of the 2 norm. So basically, the minimum norm point in each one of those cases corresponds to the intersection. So here's the minimum norm point there. Here's the minimum norm point here. And so on and so forth. So the claim, and this is really interesting, and it was Fujishige who realized this, that in each of those cases, those green points, basically, once we've got those green points, we can just read off the solution to the submodular function minimization problem. But at the same time, this algorithm, or the procedure, this is just a very simple convex. In fact, it's even simpler than, it's a quadratic programming problem. It's not even convex. Minimizing a quadratic subject to convex constraints. So what we want to do is then prove why this gives us the minimum. Prove why x star gives us the minimum. We're actually not going to go over great detail the actual algorithm to do the quadratic minimization, since it's a fairly general purpose quadratic minimization procedure that happens to be made very, very easy thanks to the fact that the function is submodular and thanks to the fact that we can get extreme points very easy using Edmonds' greedy algorithm. So the greedy algorithm is really what saves us and what makes it efficient. But it turns out that the minimum norm point still to this day is, if you want sort of a general purpose algorithm for doing submodular functions, not for any special cases like graph cuts or something else, but if you want a general purpose submodular function minimization algorithm, minimum norm point algorithm, in practice is still probably the best choice. This is in general when you don't know anything about the submodular function, like it's an oracle function. So we'll start on Wednesday talking about this algorithm. But feel free to read the slides. And after that, we'll talk about the Lavash extension. And then we'll, interestingly enough, relate the minimum norm point algorithm for the Lavash extension. Lavas extension. Okay, well, thank you very much. I'll see you on Wednesday.